we have a difficult task to talk about AI and medical imaging in a short time. So I will try to keep it between 30 minutes and less than 40 minutes, such that we have enough time for Q&A. So there's of course a lot of, and the audience is mixed. So I didn't know should we go in detail or not. So I don't go in detail. We will keep it at the general level and hopefully provide some value. So as Amelia mentioned, so I come from University of Waterloo, where I direct the Kimia lab, and I'm part of Waterloo AI Institute and affiliate to the Vector. My work has been since 1993 using machine learning techniques for medical images. So our motivation is, when we look at our southern neighbor, which is 50% of the world market basically. That's why we look at US. There are 12 million diagnostic errors a year. So Canada is comparably 3 to 5% of those type of numbers. And 20%, 28% of the diagnostic mistakes can be fatal and may result in death of the patient or even permanent disability. So just as an example, for breast cancer, misdiagnosis costs almost $4 billion a year. So when we look at the economic side of things. So we have many modalities in medical imaging, as you can imagine, and many of you are working with some of them, from MRI to CT to ultrasound to X-ray to light microscopy to OCT, many different modalities for different body parts for different purposes. So more than 700 billion images, again, in US alone. So you can double and triple that number and you get the number globally, how many images we have per year. So misdiagnosis is clearly a problem in medical imaging. So when we look at an X-ray, and the question is if there is a nodule, and usually if we miss that, we will be accused of negligence. So there was a nodule and we didn't see it. And the negligence is basically we failed to diagnose, as radiologists fail to diagnose. There are different types of error. It could be scanning error, so radiologist fails to fixate in the area of interest, or it could be recognition error, so radiologist fails to detect the lesion, or it could be decision-making error, which is most of the time, I don't know, is it benign, is it malignant, is it something that we should be worried about or not? So that's, as an example, 85% of cases that we send for breast biopsy come back negative, which is great. So that means the patient didn't have cancer, but from efficiency of the healthcare system, this is really bad. But we cannot reduce that by jeopardizing the life of the patient. So what is the source of all problems, or almost all problems, in medical imaging? So when we look at this prostate MR image, so we have to mark the prostate, for example, for diagnostic purposes, we want to calculate PSA density, or for treatment, for focused ultrasound. So we give that to radiologists or to another type of experts, and they will draw a contour around the prostate. That's segmentation, basically. So if I give it to another doctor, he or she will do another one. If I give it to the third one and fourth one, so they will draw different contours. So they will draw different segments. And the question is, well, prostate is clear. So why people are drawing different segments around the prostate? So that's observer variability. So if you look at this image and we gave it to 7 oncologists to draw it, and even if you ignore the inner 2 ones, which are really off, it's really scary that somebody draw those 2 as the prostate. Prostate is supposed to be an easy case. If I have so much variability, so much disagreement, and then we go, let's say, for radiation therapy, and the tumor area, let's say, is the red area, and then we are radiating the tumor to kill the tumor. So if those contours are not accurate, not only we will miss the tumor part, we will also hit the healthy part. So that's very serious if we cannot agree where the prostate is. And prostate is arguably one of the easy cases. Prostate segmentation is not the tough things to do, at least for the radiologist. So inter-observer variability, the difference between doctors, which is error. There's a lot of literature on the clinical side. Prostate 18%, bladder 32%, abdominal 40%, breast cavity 45%, up to lung nodules 50, the scary 54%. Basically, there is no agreement. So, and the question is, okay, what do we do? Well, some hospitals do ask two and more experts, but we cannot afford to put more than one expert on a case. Looking at this X-ray, chest X-ray image, for example, the question is there a pneumothorax? Has the lung collapsed in this image? If I show it to multiple radiologists, I will get no, yes, no, yes. So the sensitivity for pneumothorax is below 50%. So in more than 50% of the cases, when somebody's lung has collapsed, we miss it because it's a small part. It's not a huge collapse, it's a small collapse, and the contrast in X-ray images are not large, so we miss it. The radiologists will miss it. So what is going wrong in the medical imaging? Why is that the source of problem? Well, it goes wrong, and then we get misdiagnosis. So and then if there is a misdiagnosis, even if we correctly diagnose, we still is not guaranteed that we have the proper treatment plan. So how do we plan the proper treatment for any type of condition? So what is the reason for this variability? Why we cannot agree? Why the doctors cannot agree? They are all smart people. They are very knowledgeable people. Why the information is imperfect? The image information is not perfect. So the pixels have a lot of errors in them. And the complexity of diseases cannot be underestimated. Besides, the human perception is very subjective. So there is no way that we can get to 100% agreement all the time, or for difficult cases at least. So what are the consequences of these problems, the interoperability and misdiagnosis and improper treatment planning? Well, you get a lot of side effects for the patients. We get prolonged treatment, reduced patient throughput, and a lot of financial burden for the patients and for the healthcare system, doesn't matter public healthcare system or private, and of course legal ramification for some of the people involved. So it's a huge problem. So, and of course everybody's talking about precision medicine. So how do we predict what treatment protocols are likely to succeed on a patient based on various patient attributes on the treatment context? So it's very important for us to move toward precision medicine. How can we do that? So of course, clearly without using big data and computer protocols, and most likely without AI, it's unlikely that we can move strongly in that direction. So what do we call AI? So what do we call AI is basically the capability of computers to learn. And that learning could be supervised, unsupervised, weakly supervised. And the supervised learning is fundamentally either algorithmic, you have a set of steps, or is topological, which means you have a network type of stuff that you train and then you learn. If it is unsupervised, basically you group things together, you group images or patients together, clustering, or you search for something. So that's unsupervised. And if it is weakly supervised, you're basically working based on interaction between software and the radiologist and the pathologist or any other human expert. So supervised is, there is a teacher, that's labeled data, which means we need a lot of images that the radiologist or pathologist or oncologist or any other medical expert has to label. It has to delineate, highlight those regions of interest. If it is weakly supervised, we don't need label data, but we need some sort of feedback. Is the software doing its job? So reward, some sort of reward and punishment. And if it is unsupervised, then you can just go to the PACS, to the Archive of Medical Images, and apply your techniques on the raw data. Clearly, our preference is unsupervised learning, which everybody says is the future of AI. So unsupervised learning. AI is a big field, everybody talking about AI. Machine learning is a small part of it actually, but very successful. And artificial neural networks are inside the machine learning. And there are other machine learning techniques like support vector machines, classifiers that have a mathematical foundation. Decision trees, very old, random forest, a variation of that in recent years. Natural language processing, systems like BERT, very BioBERT, and so on, very capable NLP solutions, fuzzy systems, meta-heuristic optimization, and so on. What we call, most of the people call AI these days, is deep learning, which is just a small part of artificial neural networks, which is a small part of machine learning, which is a small part of AI. So just one has to be clear where we stand and what we are doing. So give you some examples what people are doing with that. Again, we want to use machine learning techniques to do some sort of identification in any type of medical images, and ideally intelligence has to be modality independent. It should be applicable on any modality. When we look, for example, semantic segmentation in knee MRI images using deep network, you see that different parts in the knee MRI have been segmented. MRI images are usually good images, they are rich, they are sensitive, but that makes their segmentation actually more difficult because there is a lot of information in them. Multi-organ segmentation using fully convolutional neural networks. So you have the ground truths. The ground truths usually on the left has been created by the expert, by the human expert, and then the network is trained based on the ground truths to learn to segment multiple organs at the same time. So very, very useful for many type of measurements. UNet is one of those specialized convolutional neural networks that is very popular these days, and it uses the concept of downsampling or upsampling. Here in T2 weighted MR images, a 74-year-old man, so with a specific PSA 5.15, which is above what we consider normal, and then we look at the Gleason factor grouping and what the software finds using the UNet is in concordance with the PIRADS. So is good for UNet and other deep learning techniques to provide this type of results. Other approaches to use deep features, which is we put our medical images through the deep networks, we get some sort of features, and then we compare them to match and find similar cases, and then through majority vote, we come to a conclusion. This majority vote could be a diagnosis, could be good for triaging, could be an initial guess for steps that come forward. So you can also make it even more specific. Here we can separate the left lung from right lung and combine it with the entire chest, get specific customized deep features for every part of the chest X-ray image, and compress them, and then extract basically those features for image search, which we're matching because in chest we have many conditions, so matching to find similar cases could be very useful. So sensitivity for pneumothorax, again, is below 50%. Using this type of concept, you can easily double that, get close to 80% when we look at the area under the curve. So 80% area under the curve is not a lot, generally, but when we remember that for pneumothorax, the sensitivity of the radiologist is below 50%, having 80% sensitivity using software is really good, is a good start. So another example is when you deal with large images like whole slide images in digital pathology, and multi-instance learning is one of those promising techniques that you can basically break it down in small parts that are malignant and benign. So whatever you use it that you want to train, and then you train a network based on weak labels. So this is one of those tricks to avoid requiring large amount of data, large amount of label data. And when we look at the RC curve, I'm hoping that all of you know RC curves and the concept of specificity and sensitivity, which is we want to get actually to these corners 100%, so being 100% sensitive and 100% specific, which is in many cases not possible. But when we look at the prostate case on the left and breast case in that paper, using 44,000 samples from Memorial Sloan Kettering Hospital in New York, very promising results. So they are proposed to use this in Nature Medicine for triaging, not even for diagnosis. So how can we make AI learn histopathology, for example? That's quite an agenda. So if I give the biopsy sample here on the left, and we get some mosaic using some technology like Utixel, and then we look at the hypercellularity and make that smaller to come up with a cellular mosaic using unsupervised learning, which will go after identifying any tissue type, which is very extremely useful. So what type of tissue do I have this image? The computer can find them, but it cannot tell you what it is because this is unsupervised. It doesn't know, is it epithelium? Is it connective tissue? Is it nervous tissue? It doesn't know, but it knows this tissue and this tissue belong together. So you can train such a network to learn histology or to learn histopathology. It's like a digital residence, basically. So when you use deep networks off the shelf, so networks that have been trained with non-medical images, and that's very common to use networks that have been trained. DenseNet, InceptionNet, ResNet, EfficientNet, many networks that you can use. And they have been trained with non-medical images, usually with ImageNet. So then you apply it on 32 type of cancer here, as you can list, the abbreviations here on the right. So for example, PRAD, prostate adenocarcinoma, or mesothelioma from lung, or kidney renal cell carcinoma, and so on, or colorectal adenocarcinoma. You see that things are quite messed up, although the network is really a good network. Now, if you train with medical images and specialize, you get this. So you can nicely separate 32 different subtypes of cancer, and suddenly you see that, for example, glioblastoma here and low-grade glioma as two different subtypes of brain cancer are well separated. I see that bladder cancer has some similarity to breast cancer, but they are well separated, and so on. So when we customize, when we teach deep networks with medical images, they learn to really separate them, which is of course very useful for both for diagnostic purposes and for treatment planning purposes. One of the things that the research community has started to look at is the usage of natural language processing and medical imaging, which is extremely important and which is one of the major components of future of medical imaging. So how can we use NLP in that regard? So in medical images, every image comes with some sort of reports and note and annotated data. This could be on radiology information system RIS, it could be on lab information system LIS, it could be anywhere beside of PACS. So either you have on the left, you have unstructured report that the radiologist or pathologist in this case has written a report, and every expert writes a different type of report. Or on the right, you have a synaptic report, which is structured. So you have a template, and increasingly, associations like American College of Radiologists or pathologists are pushing the concept of synaptic reporting forward. Probably within the next few years, it will be adopted largely. If you have structure, that's relatively easy to use. At the moment, we don't. So natural language processing can be used to categorize those reports and notes that are attached to the image, that describe something in the image. It can help us to auto-generate reports. That would be something really amazing and exciting to do if the software can look at the image and generate the report. So that's what the radiologist does. That's the pathologist does. Do we want to replace them? No. But at least we can generate the first template for them so they can edit it and save some time. So they will still be in charge. They can still sign off. They can still say, no, that doesn't make sense to me. I want to do something else. Conversational AI is, of course, very important. If we give the possibility, the interface to the medical imaging expert to communicate with computers and say, okay, give me images that contain this and that. Go to the part of the image that contains the lesion. Give me snapshots of salient features. So can the human expert interact, converse with the AI? If you look at, for example, these pathology reports, we can do a lot with those type of reports. We can get keywords, we can get topics, we can understand the relationships, provided we have enough reports, provided we have a large repository of reports. So if we can do that, all this information can be attached to the images. So now we have text that is human knowledge, that is expert knowledge, and then we have the pixel information that we can process with deep networks and other machine learning techniques. So that's a new thing. This has not existed before. So some people have looked at not just using images here, for example, annotated WSIs, whole slide images, which are digitized biopsy samples. People usually use just images to train a network, like here, a dictionary approach. Now, you can also not just images, you can also use reports. So how can we make computer understand that this is the image, this is the report, all information here, understand both of them at the same time. So this, and when we go online, of course, when you go online for the new patient, there is no report because the patient is new. He or she has not been diagnosed yet. So not only the image is available. So it's very important that we exploit every piece of information that we have. Also very exciting, the clinical report generation. So we see here these two images. The black text here is the actual report from the human expert. The green one is generated by the computer. For example, we see the nuclei are severely pleomorphic. If I look at this image, I see that the cell nuclei have really different shapes. And the first line of the automatically generated report is also the nuclei are severely pleomorphic. That's amazing. That's very good. It's a simple case. We are at the beginning of a very long road. We will not get there within the next 2 years. We need more time than that to do this. But automatic report generation based on the image information and previously evidently diagnosed cases is definitely a big part of medical imaging. Another exciting thing which should happen in every lab, which should be part of triaging, which should be in the emergency room, which should be in a small clinic, is image captioning. So the image comes, and you have seen all those applications. You get an image from your dog, and the computer writes, a dog playing in the park, and everybody is smiling because the computer now is suddenly so smart. Why we cannot do this for medical images? Of course we can. So if I train a proper network, I have text annotation, I have attention, which is the network has to find out what part of the image, which clusters of pixels are important for that diagnostic case. And then you generate the caption, left apical small pneumothorax, and small left pleural effusion remains. So if you can generate captions like this is not a report. This is 2-3 phrases or one simple sentence. This would be immensely valuable for triaging, for the technicians, not the radiologists, not the pathologists, not the oncologists, the first line of defense when the patient comes. And we can display something meaningful that can help the radiology department to set the priority for different patients based on the first estimate. We don't need to fully trust this at this stage. The experienced radiologist will come and take a look and say, no, that was nonsense. This is not necessary. If the false positive is not too large, this will be very, very valuable. But if it fails in 80% of the cases, it will be annoying and it will not be adopted. So what is the ultimate solution for observable variability? So I cannot overemphasize this, that the main problem of medical imaging fundamentally is observable variability, both inter-observable variability and intra-observable variability. If you show an image to the same doctor and says, is pneumothorax, is a lung nodule, and after 2 weeks, you show the same person the same image, and he or she may change his opinion. So, no, there's no pneumothorax. No, there's no nodule. And then you say, are you kidding me? You told me. Well, this is intra-observable variability. So there's no even guarantee that the same doctor makes the same diagnosis. And that's the scary part. So what can AI do with this medical images such that we can get rid of the observable variability? So we can classify images, yes and no, staging, grading. We can generate fake images, which could be good for training. So generating fake images is a new field. We have worked in the past in medical imaging with the so-called phantoms. We had synthetic images, but very primitive. Now we have immensely powerful techniques like adversarial generative models, and we can generate really authentic images. What can we do with them? We can segment images, we can measure stuff, and we can, of course, search. We can search and match input images in an archive of medical images. Some of these techniques are supervised. Some of these techniques are unsupervised. If you go supervised, you have to be clear about this. You need label data. You need many human experts to sit down and mark what is important to you in the image. That's very tedious. That's very time consuming. It's subject to variability itself. Bring in bias. Where are the images coming from? And so on and so on. At my lab, we love unsupervised techniques because they don't need that guidance. They just go in and try to figure things out, which according to everybody in the AI, unsupervised is the direction of future. We have to go unsupervised. So if we give this biopsy sample, which is thymoma, to a pathologist, the pathologist will give us this. After 30 minutes, 1 hour, 2 hours of examination under the microscope, or if it is digitized on the computer screen, he or she will write such a report. If I give it to the computer will tell me that's thymoma. Okay, so what? What should I do with it? Well, why? How? What are the uncertainties? What are the ambiguities? Measurements? Recommendations? The concept of classification in itself, as the most powerful, most successful AI concept, is very limited in the medical field. It may be very impressive outside of medical field, but you, as a computer software telling the human doctor that this is thymoma, he looks at it, she looks at it and says, I know, but I have to write a report and justify it. And I have to also recommend a treatment. So just telling me this is thymoma, every resident sees that this is thymoma. I don't need the computer to tell me that this is thymoma. So can you justify it? Can you elaborate? Well, not at the moment, unless we have access to the reports, and NLP can be trained for that. So why search? Image search could be an alternative solution. So if I have an image and I send that image to the large archives I have, most of the time in terms of modalities that we have would be a PACS. If the PACS is indexed, and then we can find similar images, and we bring back similar images. So what? We show these images to the radiologist and say, look, these images are similar. So what? I see that they are similar. What's your point? Well, the point is that these images come from metadata. We have the radiology reports, we have the treatment plan, we have the outcome. We know what happened to that patient. We know evidently what happened to those patients. So the images them alone have not much value. But the images along with the metadata has a lot of value. This is as if these 3 similar images with the reports represent 3 other colleagues who are sharing their knowledge and wisdom with me. So, and the search query can be anything. How can search help? You can input a biopsy sample. You can input the entire gigantic image or a volume. You can input a small part of the image, a tissue sample. You can input a region of the image. So we don't have this at the moment. We don't have this technology, which is very strange. When each one of us, every morning that we wake up, each one of us use search techniques on the internet, on our laptop, and our cell phones many, many times during the day. But we don't have all these possibilities in the hospitals, which is very strange. So we have to make that happen. This search will be a gigantic part of medical imaging of future. So now, if you use search, then the concept of virtual peer review is a given. So if you are in doubt and we can afford it, we call another doctor, we set a session. Sometimes we send the images to another hospital, we send the biopsy sample to another hospital, and wait for another colleague to give us a second opinion. We are doing that for difficult cases. Can we do it virtually? Can we do it computationally, not physically? So if an image here, that's a thyroid biopsy sample. If I don't know what that is, and I send it to an image search engine, I said, I don't know what that is. Have you had a case like this? Can you go inside search and find the top 3 similar cases for me? And the computer goes and search in the archive, in the PACS, in the LIS, and bring back the top 3 similar cases. And you see that similar is a very tricky concept in the medical imaging. It's not the shape of the sample. You have to go in detail. You have to zoom in to see why they are similar. And of course, when I grab the similar, they come with reports. We know everything about them. We know that the patient passed away or the patient was healed and was released. We know that. We know the outcome. So there is one doctor who gave me that image to search, but these other cases coming from other doctors. So is virtually you are asking your colleagues, you are inquiring into the knowledge of your other colleagues, what is this? So we are tapping into the same knowledge, and that's the beauty. That's the beauty of using AI for search. That's what I like it, because AI becomes a facilitator. AI is not generating the knowledge. AI finds the knowledge. The knowledge comes from humans. So it's interpretable. Nobody can contest it. That's my esteemed colleague, Dr. Smith. Everybody knows him. He's a good pathologist. Makes things, at least in short term, for the next 5 to 10 years, a lot easier. The question of explainability disappears. Everything is explainable. So, which means if I have a query image, doesn't matter what that is, X-ray, CT, MR, whatever. If I find the top N similar cases, if you have a large archive, I will find the top 50 images, top 100 patients that are similar to your patient. Along with the reports, I can process the images, I can process the reports using NLP, so I can find a computational consensus. So this is where we talk about having a solution for observable variability as the source of almost all problems in medical imaging. How can we do it? If you create a consensus. How do you create consensus? You have to bring many experts to the same table. But we cannot do that physically. Okay, let's do it computationally. Let's do it virtually. If we have access to large archives of images, we can do this. So just give you a high-level comparison. I'm assuming that many of you know these methods from the AI. Of most common AI techniques, just a very high-level overview. So, for example, one of the oldest one is Kimia. It's a very simple technique. It's categorization. Groups, images, text together. Just say, these images are very similar to each other. These images are very similar to each other. It's an unsupervised technique. Operates on raw data. Needs moderate level of data. And the accuracy is moderate to high, and it's very easy to design and train. So if I'm starting on AI, I will start with something simple like that. I won't go really full-scale complex. If I look at the so-called CNNs, convolutional neural networks, which are cream de la cream of deep networks at the moment, they are supervised. They need labeled data. They need lots of labeled data. The data set is immense. You need thousands and thousands and thousands of cases such that the computer can learn. So the accuracy is very high, which explains why deep networks are so successful. But they are also very difficult to design and train. They are very tricky. You need a lot of experience to do it. I wouldn't jump on CNN if I'm a newcomer in AI, but I have experience in medical imaging. I would start with something simple, then go through things step by step. So what are the challenges of using AI in medical imaging? I see 3 challenges. So first, lack of publicly available image repositories. Second, lack of publicly available image repositories. And third, lack of publicly available image repositories. We do not have publicly available image repositories. That's a big problem in medical imaging. So it took RSNA many months to create a data set for COVID-19, which is still, last time I checked, still not as easily accessible as AI community would like. So as soon as we don't have the coordination between hospitals, research units, governments, maybe companies to create large archives, then we cannot exploit AI. So we need clinically relevant cases. We need DICOM images and metadata. Otherwise, there is no exploiting AI. They have to be large enough. You cannot work with 100 images. You cannot work with 500 images. So give you an example. Pathology image, we use National Cancer Institute TCGA portal, 33,000 images, biopsy samples, break them down, 2 million images, augmented, we got to almost 15 million images. 1,000 by 1,000 pixel color. 15 million, okay, now you're talking. Now you're talking. So you need immense level of data. They need to be labeled by several experts, not just one. Not just one. Because then you have the bias of one doctor. So that doctor could be a good doctor, could be a bad doctor, could be a lot of intra-observer variability. They need to be labeled, processed by several experts. And of course, those repositories have to be curated by experts, by radiologists, by pathologists, by cardiologists, whoever the expert is. Okay, what about scraping images from internet and then some AI enthusiasts will label them? No, absolutely not. This is pseudoscience. This is not serious science. Nobody should touch medical images to curate a serious repository but the medical experts, radiologists, pathologists, oncologists, cardiologists. Not engineers, not computer scientists, not AI enthusiasts. I would not touch those. This, again, I'm not exaggerating. I consider data sets coming from internet. Yes, they go and scrape it from radiology journals. Yeah, but this doesn't make it reliable. It's not DICOM. No radiologist guided the data acquisition. So it's paramount that the data is curated by medical experts. There is a lot of information online. So if you're getting started on the AI side, there are many actually good videos, courses on the internet from MIT, from Berkeley, from Stanford, and some also from Canada. So if you want to look and learn, there's a lot of information, but you have to be careful where you're listening. So listen to the expert. Don't just it's amazing that there's so much interest. But if you want to learn something, you have to learn from experts. And of course, the ethics of medical imaging is immensely important. We didn't have time to talk about ethics. I just did last year a video for Department of Medical Imaging at Western, talked about ethics of medical imaging. So if you're interested, you can look it up and go in detail. So I guess I stop here. I apologize if it was too fast. I wanted to save time for some questions and answer. Thank you so much.
All right, thank you so much, Dr. Tizhoosh. That was amazing. So we actually got a couple of questions. So the first question is, in AI for search, WSI are given as input. It may have a lot of stroma and normal region along with the tumor region. Do you think it will affect the retrieved images and the reports, and how could you overcome this?
Very difficult task, yes. When you don't have labeled data and you have different structures, different tissue types in a whole slide image, which is a digitized biopsy sample, the computer will go and group them together. This is a stroma, this is fat, this is debris, whatever it is. It doesn't know the label, but it says this belong to each other. The purpose of search is targeted. So if the input is coming from the expert and says, okay, I marked this region, which is hypercellular epithelium, then the software will go and find matches for that. The software that has no clue what hypercellularity means because it's working in an unsupervised way. But you can guide it. As the human expert, we can guide it. And that's the nice things about it. So we can combine that. There are concepts of collaborative learning, partner learning, multi-instance learning, multi-magnification learning in that context that we have to combine to make that happen. There are several challenges still remaining. But generally, using unsupervised technique come with some price tags. Yes, we don't know what it is. But if the search is guided regionally, it will go and get the information that you're looking for.
Amazing. So our second question, will AI completely replace human experts in medical imaging?
I don't think so. Not within the next 10 years, I would say at least. And if so, the duties of the human expert has all been shifting. So we will shift more toward research, toward deeper level of understanding of the images, and we will delegate a lot of hard work and handiwork to the machine learning and AI. But as long as we do not have the next generation of AI, as long as the Turing test is valid, we do not have anything better than Turing test. And according to Alan Turing, still the human operator is the ultimate validator of AI. As long as this is true, which I don't see it being changed for the next 50 years. So as long as this is true, which means only humans can tell whether a computer is smart or not. As long as this is true, so there will be no way for computers to replace humans in any field. They will take away of a lot of tedious works, which is fantastic. But as a patient, I have been working with artificial neural networks since 1993. As a patient, I still want a human operator on my bed when I'm a patient. So, and I want to use the full AI, but the human operator, according to Alan Turing, is the ultimate validator. That's what matters.
That definitely makes a lot of sense. So we actually have a question from Dr. Nick Bontes. He asks, who owns the medical image in Ontario right now, and should the patient have access to their own medical images?
Yeah, that's a difficult one. There are different rules. Basically, every hospital has access to its own archives, PACS, and other radiology information system, hospital information system, and so on. And not even hospitals exchange easily information with each other, let alone exchanging with non-medical field, let's say computer science. So there are initiatives ongoing. There are clusters being initiated such that we can combine. There has been an initiative in Ontario, as far as I know, that all hospitals had to contribute to it. We have millions and millions of medical images stored in specific repositories in Ontario. but nobody has access to them because we don't have the regulations. We don't have the laws. How do we protect the privacy? What do we do with those cases when retrospectively we have to go? Should we go retrospectively ask the patients, or we don't use them and from now on we use them? There are a lot of information questions regarding patient privacy, but also what people don't talk about it, IP is a sticky point. So I talk to many radiologists and pathologists, and they say, if I give my images to you as a computer scientist, and I have put my knowledge, my entire knowledge and expertise in those delineations and contours and markups, that's my IP. What happens if you come up with a software? Yes, that's true. You have to come up with a new understanding of IP and the innovation. There is no AI without data. Data comes from hospitals. So that's new. That's absolutely new. And we don't have a framework for that either. These are factors that prevent us from having those largely publicly available repositories.
Absolutely. I feel like regulations and policies are definitely playing catch up to technology a majority of the time. So I think we have time for another question. So as you mentioned, trust in computer vision is very important to the application of AI. So other than these searching approaches that you discussed, how would you propose to develop trust and trustworthiness in the technology?
There is a simple way. The medical imaging is the only way. You cannot come up with a product unless it's validated. There should be publications for that. There were companies like Tyrannos, they got other business. How can you have a company? There is no paper published in clinical journals. So there is no product in medical imaging unless you validate at different hospitals, you publish papers, you discuss it within the research community, you talk about deficiencies, you validate again, you do external validation and internal validation with different data sets, look at the variability of the data, publish more papers, more white papers, discuss more, and then you can approach the regulatory bodies like Health Canada and FDA and say, now we have a product that has gone through validation, is reliable. Companies cannot do it alone. Research units cannot do it. This is not going to happen without radiology department and pathology departments.
Absolutely. Amazing. Thank you so much, Dr. Tizhoosh, for taking your time today and coming to share your expertise on AI and medical imaging. It's definitely a growing field. For sure, we can definitely see a growing adoption rate in the field of AI using artificial intelligence. So, all right, guys, if you signed up for the next session, we'll be letting people in at around 3:55. Thank you guys so much for coming, and we look forward to see you soon.
Thank you very much, everybody. Pleasure to be with you.